now we'll talk about estimation. Estimating a population proportion is the first thing we're going to do, but let me generalize that. What we have is we'll be looking at a population of things, population. And this population is going to have certain parameters. The parameters may be a population proportion, like the proportion of Democrats, or it might be a mean, like the average age or something, or it might even be um, the standard deviation or the variance. So this population has certain characteristics that are unique to this population, all right? Now what we're going to do is we're going to take a little sample of this population. So we're going to take a little sample of this population out. We're going to take out a sample, and this sample, we're going to use it to guess at these population parameters. So we have the population parameter p, mu, and sigma squared. And in the sample, if I want to find a guess for p, I'm probably going to use p hat, which is the sample proportion. All right. If I want to guess for what mu is, I'm probably going to use x bar, which is the sample mean. And if I want to guess at what sigma is, I'm probably going to use s squared. So if I want sigma squared, I use s squared. If I want p, I'll use p hat. Mu, I'll use x bar. So that's what we're doing. We have a population. We're going to try to estimate what one of these numbers is. And unless we do a census and collect the data from every single thing and every single element of the population, we can't actually calculate these numbers over here, p, mu, and sigma squared. So what we usually do is we take a subset of the population, a sample, which is usually easier to handle. It's usually an easier thing to do. And we find the sample statistics that correspond to those population parameters, and we use those as our best guesses. That's what we're going to endeavor now. All right, so let's see. The first definition we want to look at is the definition of a point estimate. And a point estimate is a single value or point used to approximate a population parameter. All right, so we have the population with its parameters, and we want to estimate that population parameter, and we're going to use a single number to do that. So the sample proportion p hat is the best point estimate of the population proportion p. So if I have a population and I want to estimate its proportion, what I do is I take a sample and I find the proportion for that sample. That's going to be p hat, and that's going to be the best point estimate for p. The next thing, the sample mean x bar is the best point estimate of the population mean mu. So I have a population, I want to guess what the average something is for that population. So because it's usually not feasible to get information from the entire population, I take a sample of that population and I calculate the mean of that sample, and that is going to be my my best guess for the mean of the population. And the sample variance s squared is the best point estimate of the population variance sigma squared. All right, so these are point estimates. They're single number guesses or approximations, um, estimates for the population parameters. Now, the problem with a point estimate is that a point estimate, we can have zero confidence in a point estimate because a point estimate is a single number. So for instance, if we were talking about the average age of all men, well, the population of all men is a huge population, so it would be impossible for me to actually calculate mu because I'd have to look at the age of every single man alive, and then I'd have to find the arithmetic mean, and that would give me mu. Because that's not really a feasible thing to do, get the population mean, what I would do is I'd get a sample of men, a representative sample that would represent, pretty much all men in the world, and I would find the mean of that sample, and I would use that sample mean to estimate the population mean. Now, let's say I get an average age from that sample of, I don't know, 35 years of age, right? Well, I can have zero confidence in that guess because, I mean, men range in age from 0 to infinity. I mean, technically, a man could live any age from 0, and there's no upper bound on the age of men. So it could technically be any number from 0 to infinity, which is an infinite number of single digits or single numbers. It's an infinite uh, number of outcomes. So a single outcome from that infinite number is kind of 30, exactly 35 is the average age of all men. There's no confidence in that. So in order to give some confidence to my estimate, in order to make my estimate a little bit more reasonable, what I do is I create an interval estimate. Instead of giving a single number for my estimate, I'm going to make a range of values be my estimate. And that's where we get this definition, a confidence interval. A confidence interval, or an interval estimate. Notice up here we have a point estimate. Now we have an interval estimate. So an interval estimate is a range or interval of values used to estimate the true value of a population parameter. A confidence interval is sometimes abbreviated CI. All right, so we have a confidence interval which we will abbreviate CI. All right, so now the next thing I want to look at is the definition here. And the definition of a confidence interval. After the definition of a confidence interval, I want to look at the definition of a confidence level. Now, the confidence level is the probability which is found by subtracting alpha from 1. So the confidence level is 1 minus alpha. But the confidence level is the probability that the confidence interval that we create does actually contain the population parameter, assuming that the estimation process is repeated a large number of times. All right, so what does that mean? Well, we have a huge population, right? We have a huge population, and we can't really do a census to get all the information from the population, but we have this huge population. And what we're going to do is we're going to create an estimate based on a sample. Well, there's many samples that I could take. Let's say I take this sample, right? This sample, this sample from my population is going to have its own mean and standard deviation, all that stuff, right? So let's call that x bar 1. That's the sample mean from the first sample. Let's say we take another sample. That sample is going to have its own mean. This is sample, let's call this sample, this first sample, sample 1, and the second sample, let's call it sample 2, so that its mean is x bar 2. So what we would, if we took samples, we would each get different sample means. If we took two different samples, and if we created a confidence interval based on that sample mean, we get two different intervals. So what the confidence level is, if we did this 100 times and we found 100 different confidence intervals, the confidence level is the probability that our confidence interval actually would contain the population parameter. So if we did this 100 times and created 100 different confidence intervals, the confidence level would be the proportion or the percentage of those confidence intervals that we created that we would expect to actually have the true population mean. So for instance, if we said that the confidence level, I'll abbreviate it CL, was 95%. Let's say we say the confidence level is 95%. Well, if the confidence level is 95%, that means if I created 100 confidence intervals, I expect 95 of those confidence intervals to actually contain the true mean. So that's what the confidence level is. It's the probability that the confidence interval we create will actually contain the true population parameter. All right, the next thing we want to look at is the critical value. And a critical value is the number on the borderline separating sample statistics that are likely to occur from those that are unlikely to occur. All right, what that means is the number z of alpha over 2 is a critical value that is the z-score. It is a z-score with the property that it separates the area of alpha over 2 in the right tail of the standard normal distribution. So this is what we're talking about here. We read about the standard normal distribution here. That's the bell curve. And what this says is that the critical value, which we call the z of alpha, let's write that out, the z of alpha over 2. Oops, my alpha's are not great. It's the z of alpha over 2. So the critical value, which we're calling the z of alpha over 2, is the z-score, this z-score that separates an area of alpha over 2 in the right tail of the standard normal distribution. So this area over here is alpha over 2. So that area over there is alpha over 2. And the z-score that separates that area from this area over here, which is 1 minus alpha over 2, the complement, the z-score that separates the alpha over 2 tail up here from the 1 minus alpha over 2 area over here is called the critical value, all right? Now, let's use that information to do a problem where we find the critical value. So in exercise 5 through 8, what we want to do is we want to find the critical value indicated. So in example 5 through 8, in exercise 5 through 8, find the indicated z value. Find the critical value z of alpha over 2 that corresponds to a 99.5 confidence level. So remember I said earlier that alpha is actually 1 minus our confidence level. So we have the confidence level here. Our alpha, the alpha that we're looking for, is going to be 1 minus that confidence level. So 1 minus the confidence level is going to be 1 minus 0.995 or 0.005. Now, that's not actually what we need because notice this is the z of alpha over 2. So I need to know what alpha over 2 is, not what alpha is. So alpha over 2 in this case, alpha over 2 is going to be 0.005 over 2 or 0.0025. So that's the information I need in order to find that critical z value. So alpha over 2 I know is 0.0025. So alpha over 2 is 0.0025. All right. So now I have my value of alpha over 2. I said I know that alpha over 2 is equal to 0.0025. That's the first piece of information you need. Once you know alpha over 2, this definition will tell you how to find the critical value. It is the z-score with the property that it separates an area of alpha over 2, which is this area, in the right tail of a standard normal distribution. So let's draw that out. Here is the standard normal distribution. It's a bell curve. And in the right tail up here, I want to have an area of 0.0025. So I want this area over here to be 0.0025. And what I want is I want the z-score here that separates that area of 0.0025 in the right tail. So let's see. Oops. Let's see what that z-score is that separates 0.0025 in the right tail. So there are a couple ways that we can actually do this, all right? One of the ways of doing this is to go ahead and use table A2. The other way of doing it is to use the TI 83 or 84 calculator. So let's go ahead and pull that up. Okay, so in order to find that z-score, what we're going to do is we're going to go into the TI 83. We're going to actually go, and what we're doing is we're looking for a z-score given an area. Now, if you remember, the inverse norm function that we're going to use, we're going to go to second, we're going to go to distributions, and we're going to use number 3, which is the inverse norm. This function actually takes the area to the left of the z-score, and it'll give you the correct z-score. But we don't have the area to the left. What we have is the area to the right. So we need to calculate the area to the left. Well, if I have 0.0025 on the right, then on the left I have the complement of that, which is 1 minus 0.0025, and that's the area to the left. So into the calculator we actually have to put not the area to the right, but the area to the left. But we can put it in this way. We can actually put it in as the inverse norm. See, we have the inverse norm there of 1 minus 0.0025, and that will give us the critical z value that we need. So our critical z value is 2.81. We want to round z-scores to two decimal places. So the number we're looking for for problem 6 is 2.81. All right, so here, this z of alpha over 2 that we're looking for, the z of alpha over 2 is actually equal to 2.81. And that is the answer for number 6. All right, so we want to do the exact same thing for number 8 here. So we have the answer for number 6. The answer for number 6 is this 2.81. Now we want to find the critical z in number 8. So in number 8, it just says find the z of alpha over 2, and this one is presented to us in a different way. See, in this problem, they gave us a confidence level, and they gave us a confidence level, so we had to find alpha by subtracting the confidence level from 1. In this case, they actually gave me alpha already, so there's less work here. They already gave me alpha. I don't have to subtract anything from 1. All I have to do here is find first alpha over 2. So let's go ahead and do that. All right, so we're working on this problem here, number 8. And what we want to do is we want to find out what alpha over 2 is equal to. In this case, that's 0.02 divided by 2, which is 0.01. So now I know alpha over 2. What I'm doing is I'm going to use this definition to find the critical value. It says the critical value is the z-score that separates an area of alpha over 2 in the right tail of the standard normal distribution. So here's the standard normal distribution. We have 0.01 up here in the right tail, and we're looking for that z-score. That is the z-score that we're looking for as the z of alpha over 2, okay? That z-score. Now, if there's an area of 0.01 in the right tail, that means the complement of that is on the left-hand side here. To the left of that z-score would be 1 minus 0.01 or 0.99. So what we need to do is we need to find the z-score that separates the bottom 99% from the top 1%, basically the 99th percentile. So in order to do that, once again, we're going to use our TI, because remember, the TI-83 calculator will only take the inverse normal function takes the area to the left. So what we need to plug into that inverse normal function is the area to the left of the z-score. So I go here, and we turn it on first, clear. We go to second, then we go to distributions. We need inverse norm, which is number 3, and then we're going to type in the area to the left, which is 0.99, close the parenthesis, and enter. And this is going to be the critical z value for number 8. So for number 8, the z of alpha over 2 is equal to 2.33. So z of alpha over 2 for number 8 equals 2.33. Okay, so now we'll find a margin of error. We just found critical values. So now let's go down to the definition of margin of error and see how to find margin of error. When data from a simple random sample are used to estimate a population proportion P, for instance, the margin of error denoted E is the maximum likely difference between the observed sample proportion P hat and the true value of the population proportion P. The margin of error E is also called the maximum error of estimate and can be found by multiplying the critical value and the standard deviation of the sample proportion as shown in formula 7.1. Okay, so to find the margin of error, we're actually going to have to find critical values. That's why we went through finding critical values first. So we take the critical value and you multiply it by the standard deviation of the sample proportions. That formula 7.1 shows that multiplication. That's how we find the margin of error E. And it's also defined as the maximum likely difference between the observed sample proportion and p hat and the true sample proportion P. So basically, it's the maximum likely difference from P hat to P. So it's the maximum likely difference. This is the difference. The maximum likely one would be what we would call the maximum error of estimate or the margin of error, okay? Now here are some examples where we're asked to calculate the margin of error. Finding margin of error. In exercises 17 through 20, assume that that a sample is used to estimate a population proportion P. Find the margin of error E that corresponds to the given statistic and confidence level. Okay, so in number 18, we're given n equals 500, x equals 220, and a confidence level of 99%. All right, the first thing we have to know is how to find p hat. P hat is going to be x over n. P hat is equal to x over n. That's a formula that we're going to have to use throughout this section. So P hat is equal to x over n. And remember, alpha is equal to 1 minus the confidence level. So alpha is 1 minus the confidence level. And I think that's all we need to be able to do this problem. All right, so let's go ahead and do it. Let's move this one down a little bit. All right, so what it says here is to find the margin of error, I need to multiply the z of alpha over 2, the critical value, by the square root of p hat times q hat over n. So let's go ahead and find all those things. First, we find alpha. Alpha is equal to, well, let's first find p hat. P hat is equal to x over n. So in this case, it's 220x over 500, which is n, which gives me a value of 0.44. 0.44 is my p hat, and my confidence level is 1, or my alpha is 1 minus my confidence level, which is 1 minus 0.99, which is zero point 0.01. Actually, I need to know what alpha over 2 is. So let's find alpha over 2 real quick. Alpha over 2 is equal to 0.01 over 2, which is 0.005. So there I have my alpha over 2 and my p hat, all the things I need to use this formula. Because once I have p hat, I can find q hat because it's 1 minus p hat. So q hat is equal to 1 minus p hat, which is 1 minus 0.44. 1 minus 0.44 is 0.56. So there I have p hat, I have q hat. Actually, in the formula, I don't have alpha over 2. I have the z of alpha over 2. And remember, the z of alpha over 2 separates in the right tail an area of alpha over 2. So I want the z-score that has 0.005 over here in the right tail. So I'm looking for this z-score as my critical value. So let's see. Let's find that z-score. So we can go to our trusty TI. The z-score that separates 0.005 in the right tail has, in the left side, the left area is going to be 1 minus 0.005, or 0.995. So I'm going to come to the TI-83, and I'm going to do the inverse norm again. Second, distributions. I'm going to do number 3, which is the inverse norm. And what I'm putting in is 1 minus 0.005, or I could just put in 0.995. Close the parenthesis and press enter, and I get 2.56, or sorry, 2.58 as my z-score, my critical z. So 2.58 is what I'm going to use. All right, so the z of alpha over 2 then, the z of alpha over 2 is equal to 2.58. So let's plug all these into my formula and find E. I found everything I need to calculate E. So E is equal to the z of alpha over 2, which I just found to be 2.58, multiplied by the square root of p hat. Let me see, p hat was 0.44, right? 0.44 times q hat. Q hat, it was 0.56 times 0.56, all divided by n. And n in this case is 500. So let's go ahead and calculate E. So we say that it's equal to uh, 2.58. Let's turn this on. 2.58 times the square root of 0.44 times 0.56 divided by 500, and I close the parenthesis to close the square root, press enter, and we get that the margin of error is point zero 0.05, oops, lost the number, 0.057, 0.057. And this is our margin of error E for number 18. All right, so let's go ahead and do that exact same thing over again, but let's do it for number 20. Okay, number 20 is slightly different because in number 20, instead of having to find p hat, they actually give us p hat. Let's look at it. We need to find the margin of error. The confidence level is given as 90%, so I can find alpha and alpha over 2 and the z of alpha over 2 from just that number. The sample size n is 1,780, and this number, it says of which 35% are successes. So 35% of these things are successful. Well, that's actually p hat. P hat is the probability or the proportion of successes in my trial, or x over n. But they're giving it to me here as a percentage, so I don't actually have to find the p hat. It's given to me. So I know p hat is equal to 0.35, which means I also know q hat. Q hat is equal to 1 minus p hat, which is 1 minus 0.35. So q hat is actually 0.65. So I have p hat and q hat. Let me see. I know alpha is 1 minus my confidence level. So alpha is 1 minus 0.90, which is zero point 0.1. And alpha over 2 is then, alpha over 2 is actually equal to 0.05. So now I need to find the z-score that separates an area in the right tail of the normal distribution of 0.05. So I'm looking for this z-score right here that has 0.05 up here. Well, if it has 0.05 up here, I actually need to know what's on the left of it, right? On the left of it, if 0.05 is above, I have 0.95 to the left below. So what I'm going to do is I'm going to do the inverse normal for 0.95. So I come over here to my TI. Let's see, I need the inverse normal. So I do second distribution, then go to number 3, inverse normal. And I'm going to plug in, what is it, 0.95? The area to the left, 0.95. And I get that the critical z is equal to 1.64. So my z of alpha over 2 is 1.64. Z of alpha over 2 is equal to 1.64. And I believe those are all the numbers I need to do my calculation. So let's find the margin of error, E. So E is then equal to the z of alpha over 2, which is 1.64, multiplied by the square root of p hat, which is 0.35, times q hat, which is 0.65, time, or divided by n, which is 1780. And then we're just going to do all this on our trusty TI again. So we'll pull out the TI-83, and we're going to plug in those numbers. So I get 1.64 multiplied by the square root of 0.35 times 0.65 divided by 1,780. Close the parenthesis for the square root, then press enter. I get 0.019. So my margin of error for this problem, 0.019. So there we found two margins of errors for these two examples. Okay, so now we're ready to construct confidence intervals. Now, to construct a confidence interval, what we're going to do is we're going to take the point estimate, whatever it may be, and we're going to add and subtract the margin of error. We've only learned how to find margin of error for proportions, but in subsequent sections, we're also going to learn how to find margin of errors for means, when we know sigma, and for means when we don't know sigma. So we're going to have three different formulas for margins of error. One for population proportion, one for a population mean with sigma known, and one for a population mean with sigma not known. And once we have our point estimate, all we have to do to find a confidence interval, actually, once we have a point estimate, all we have to do is take our point estimate and add and subtract the margin of error like we're doing right here. So for instance, we're making a confidence interval for P. All we do is take the point estimate, which is P hat, and we add and subtract the margin of error. If we were finding a confidence interval for mu, we take X bar, which would be the point estimate, and we'd add and subtract some margin of error. But this margin of error is going to be a different formula than the one we just learned. And if we wanted to, well, we're not going to do it in this course, but if we wanted to make a confidence interval for sigma squared, we do the same thing. We take the point estimate for sigma squared, which is s, and we'd s squared, and we'd add and subtract some margin of error. All right, so that's a generality how to create a confidence interval. We need to know the point estimate, and we need to know the margin of error. We know the point estimate for proportion is p hat, and we just found out how to find margin of errors using formula 7.1. So let's take a look here. The objective is to construct a confidence interval used to estimate population proportion. Here's some of the notation. These are things that you're going to have to be able to recognize. P is the population proportion. P hat is the sample proportion. N is the number of sample values. E is the margin of error. We just calculated it. We just had formula 7.1. And the z of alpha over 2 is the critical z value, which we just spent a long time trying to figure out how to calculate. These are the requirements for being able to do this estimation. Basically, these requirements are mostly the requirements for the binomial distribution to be estimated as a normal distribution, as it says right here. So then, this requirement is a way of verifying that these things are true so that the normal distribution is a suitable approximation for the binomial distribution. So we're using the normal as an approximation for the binomial here. And that's what these requirements basically are about. And this is how we construct the confidence interval. We put P, the population proportion, in the middle, and we say it has to be less than P hat, which is a point estimate, plus E, and it has to be greater than P hat minus E. So we create a range of values that we assume that P is going to be in. Okay? This is how we find the margin of error. This is just 7.1. This is just formula 7.1. And this is how we create the interval. So there are all the directions right there. For instance, let me give you an example. If we go back up to number 20, right? And we wanted to create a confidence interval for number 20. Well, P hat is equal to 35%, 0.35. And we got E to be 0.019, so that the confidence interval that we would create would be P hat 0.35 plus or minus E, which is 0.019. So what we would do is we'd take P hat, we'd add E to it, and we would subtract E from it. So let me see. The lower bound for our confidence interval is going to be P hat minus E, or 0.35 minus 0.019. So the lower limit for our confidence interval would be 0.331. 0.331. The upper bound for our confidence interval would be 0.35 plus 0.019, which gives us 0.369. 0.369. That would be our confidence interval. And it would be actually a 90% confidence interval. So that means that we would be 90% confident that this interval would capture the true population proportion. So we're 90% confident that the population proportion is somewhere between these two numbers. Or another way of saying this is, if we were to create 100 such intervals using different samples and different p-hats, we would expect 90 of those intervals to actually contain the true population proportion, which is pretty good. All right, so let's do this from scratch with another problem. Let's do this from scratch with this example right here, constructing a confidence interval. All right, and what I'm going to do is I just showed you basically how to do it by hand because I showed you all the steps to doing it by hand. What I want to do now is I want to use the TI 83 or 84 plus to do it, okay? So constructing a confidence interval. In exercise 21 through 24, use the sample data and confidence level to construct the confidence interval estimate for the population proportion P. So they gave us N, they gave us X, and they gave us the confidence level. What we want to do is we want to create a confidence interval. And this little box tells us how to do it. Press stats, then select test, and we're going to select one prop z int. That is a one proportion z interval. So that's an abbreviation for one proportion z interval. And then we're going to plug in certain parameters. All right, so let's go ahead and do that. It's going to ask us for some of these numbers. So here's the TI. We turn it on. Now this is going to do all the work we just did for finding E, adding it and subtracting it. This is going to add finding the critical values. This is going to do all of that for us. So we go to stats like it says. Press stats. Here's stats. And then it says select tests. So notice above here we have edit, calc, and test. We're going to go over until we get to tests. And under tests, I see one prop z int. One prop z int. Let's see, scrolling down. That's one prop z test. That's not what they're asking for. We want one prop z int. So let's see. One prop z int is letter A. If you scroll down, one prop z int, we press enter, and it brings up this screen. Well, in this screen, we're asked for X, we're asked for N, we're also asked for the confidence level. Those are the things that were given to us. X, it says, is 400. So I put in 400 for X. That's exactly what it says here. X is 400. N it says is 2000. So I scroll down and I press 2000 for N. And then the confidence level it says is 95%. So that's already there. 0.95 for my confidence level. Then I just highlight calculate and press enter. And there it is. The calculator actually did all the work for me. It gave me my interval. My interval here actually is 0.18247 to 0.21753. So we want to round that to 3 decimals. So 0.182 to 0.217. So our confidence interval is 0.182 to 0.217. And that's all the work we just did, but the calculator did it all for us. All right. Last example. An important issue facing Americans is the large number of medical malpractice lawsuits and the expense they generate. In a study of 1,228 randomly selected medical malpractice lawsuits, it is found that 856 of them were later dropped or dismissed. Now, part A says, what is the best point estimate of the proportion of medical malpractice lawsuits that are dropped or missed? Well, we have here a sample. We have here a sample of medical malpractice lawsuits. The sample has a size 1,228. So N is equal to 1,228. And of those 1,228, 856 of them fit the criteria of being dropped. 856. So if I want the proportion of medical malpractice lawsuits that were dropped, P hat from this sample is going to be 856 X over 1,228 N. So remember, P hat was X over N. So we get P hat here to be 856 divided by 1,228 yields 0.70. So let's say our P hat is 0.70, all right? Now, we have P hat, and that is part A. What is the best point estimate? 0.7, 70%. So the best point estimate for the proportion of medical malpractice lawsuits that are dropped, 70% of medical malpractice lawsuits are dropped. Part B, construct a 99% confidence interval estimate of the proportion of medical malpractice lawsuits dropped. So part B is where I'm going to plug all that stuff into my TI to create the confidence interval. Let's see if we can find all that information. Well, let's go back. We go to on. Let's clear this. Now we go to second. No, not second. We go to we don't go to second. We go to stat. We go over to test. Scroll over to test, and then we're going to do a one proportion z int interval. One prop z int. It's letter A. So you have to scroll all the way down to letter A, one proportion z interval, one prop z int, press enter, and then it comes up with the one prop z int stuff. The stuff that we entered last will always still be in here unless you clear your memory. So we're going to have to actually clear all that stuff out. Exit told me, and the problem was 856, 856, and it told me was 1228. The confidence level I'm looking for is, in this case, 0.99, 99% confidence, and then I hit calculate. So here's an interval estimate for the proportion of medical malpractice lawsuits that are dropped. 0.663 to 0.73031. So that's 0.663 to 0.731. And this interval estimate is 99 has 99% confidence. This point estimate has zero confidence.